Yeah, hi everyone. My name is Andrej Jovanovic. I'm currently a research assistant at the CamelSys group at the University of Cambridge, and this is where I'll be starting my PhD in October. Firstly, a thank you to Harsha for extending the invite to ML Efficiency for me to give this talk. It's great to see that I'm leading the ML theory direction with Cohere in the community, but it's also cool to see that I've been here for a while and now we're getting this collaboration between two ideas that are overlap quite a bit. So today, what I'm hoping to be going through is, the title of the talk is called Communication Deficient Training of Foundation Models Through Federated Learning. And what I really want this resource to be is, it's not going to be like a researcher's walkthrough where we're going through very deep mathematical proofs and like all the underlying fundamental, like experimental configurations, which models were used and why the results are the way they are. But what I really want to do is to give a sort of brief historical overview of how we arrived to this point where we're using federated learning to train LLMs, because the jump is, it doesn't really make sense unless you saw the whole story. So for those of you that are experts in the field, this might seem a bit trivial, but at least for me, coming into this and trying to see how the chain connected was really helpful. So the agenda for today's talk is going to be a little bit like this. So first, I'm going to start with motivating why we need parallelism in the first place in machine learning and how it relates to the scale of our models that we're typically seeing in training. Yeah.
Andrew, sorry. Are you changing your slides?
Yes, I think it's second slide.
It's not moving, I think.
No? Okay.
No. Can you try resharing?
Okay, there we go. Let's see, entire screen. Great. Okay, can you see it now?
Yes, now, yes, perfect, thank you.
Right, so we're going to start with this. So I was saying, why are we talking about parallelism and why this is necessary for LLM training? Then we're going to move on from this. Once I've hopefully motivated you why parallelism is needed, we're going to draw equivalences between traditional data parallelism as a paradigm and how this extends to federated learning. Once I've done this background, we're then going to jump into state-of-the-art methods for LLM training, and which actually use federated learning under the hood. And I'm specifically going to focus the most on a recent paper that I've been involved with along with some fellow collaborators called DESLOC. And then once we've finished all of this, I'll give a forward-looking direction at what interesting research directions are emerging from this field. So yeah, let's start now with the talk, and I'm going to ask you all to go back to your first introduction into machine learning. So for some of us, this might be a while ago, but the reason why I want to start here is that when we were in these classes, we learned how to do machine learning fairly naively from an engineering standpoint. Obviously, this is a well-known choice because we need to learn about machine learning without a lot of abstractions. And the three main things that we're trying to learn about is, at least in my eyes, the main buckets that I've listed on the slide here. So the first one, we think about what model we're trying to choose. So apart from the model architecture, so we're going for a CNN, a feed-forward network, or a transformer, we're trying to make the model as big enough, right? And you can read here, size, capacity, whichever synonym you want, but we want this model to be big enough such that you can accurately predict the underlying data distribution, but you don't want the model to be too large such that you're overfitting onto the evaluations on the training set, and then you get very poor performance in generalization, right? And this is sort of the lever that you're going to be playing with, but you're not really thinking about size in terms of engineering costs, and I'll explain more about this later. Then, when we're choosing data that we're training our models on, we're basically told, like, get enough data such that your model performs well, and you just want the model to be trained on high quality data. And there isn't much specification as to what this really means. Then the final thing that we want is we're going to say, okay, we need to train our model in some way. So some models were introduced that they can be trained in closed form, such as linear regression, but then other methods, we use some sort of iterative strategy like gradient descent to do some stochastic approximation. Now, here we're told you can choose a family of optimizers, and the professor will list a whole bunch of them, but we typically go for gradient descent. And then here we say that the thing that we want to introduce is this notion of stochastic gradient descent, where we're thinking about how big our batch size is. Now, the professor will tell us we don't want a batch size of 1,000 because this is crazy and inefficient, but we don't want a batch size of 1 because this will not be a good approximation of the true gradient. We want to be somewhere in the sweet spot in the middle. And let's say we choose 32 or 16 or what have you. Now, why this is good is that the typical playgrounds that we're playing in, like MNIST and Cypher, these problems are very easy. And it is good because you will learn a lot, right, about machine learning. And the reason they're easy is that the architectures are not too big. So with MNIST, you can achieve really good results with a 3-layer neural network, and you can increase performance without changing the architecture and doing, some clever regularization techniques or pre-processing on your data. And then the data itself is not too big. So in volume, it's about 50,000 to 60,000 records. But even spatially, these are 32 by 32 pixel images with a single channel dimension because it's grayscale. Then finally, the optimization algorithm is not too intensive, right? You don't really think about how much stress this is going to put on your machine because you can do it pretty much on your laptop with the CPU, and this will train fast enough. But the reason why this is a sort of problem is because the other side of the coin is that we start taking the efficiency and the engineering of the system for granted. So we have no conception of the footprint that this machine learning workload will leave on our physical system. So at least for me in these introductory courses, we never think about model precision. We never think about how much memory footprint is introduced in training. So with how much storage you actually need or memory you need to store the activations, the optimizer states, the gradients. And then we also don't think about any considerations about, quantization for inference and what we need to do this efficiently, nor do we think about bandwidth. And bandwidth is going to be the focus of the talk here because we can process, really large batches. We can put a batch of 32 and this is fine, right? The training is not noisy. We have a good enough throughput through our system that we're satisfied with this. And underneath all of this, in the entire time, we're assuming that everything can be done on a single node, and that single node is comprised of a single processing unit. So either a GPU or a CPU. Now, for those of us that go towards language modeling, right, when you make the jump, things become exponentially more difficult, and you have to actually start caring about the engineering of the problem rather than just the machine learning, loss function, backpropagation, and so on, right? So let me paint the example for you here. So let's say we want to train a Roberta architecture on a certain problem. It doesn't really matter what the problem is. And say we have 350 milliparameter variant of said model, and we have a single GPU with a capped memory. And we want to get this training loop in such a way that the model trains and that the only factor that I have to tweak is the batch size. So what can we do? So firstly, to represent the model, we can think about whether we want to indeed represent the model in float point 32, or do we want to start going down to half precision with BF16, which is the de facto standard, yes, for training large language models, or do we want to do mixed precision training? Then observing the model itself, we are thinking about maybe how large do we want the context window of the model to be? Do we want it to be 512? Or do we want it to be 2048? Then actually training the model, do we want to do full fine-tuning, because this might be expensive, or are we trying to only isolate certain layers by freezing some or training just a classification head, or maybe doing something with low rank that is a bit more clever? Then once we've done all of this and constrained our training loop, we finally get to a situation where typically stochastic gradient descent is not going to be a robust enough optimizer. So we say, hey, I'm going to slap on Adam W because this is the de facto standard and it's really robust. But then we start asking the question, how do we store the 2 additional optimizer states in memory? And we see that now each of these decisions is going to balloon or decrease, depends how you view it, the amount of memory you're going to have in this training loop. And then finally, we arrive to a state where everything's fit, but the way I can get training to work is if I drop down my batch size to 2. Now we ask 2 questions. So the first question is a batch size of 2 good enough for our task? As in, will training be noisy or stable enough for it to make good progress? But moreover than this, on an efficiency point of view, do we have enough bandwidth? Because we're only processing essentially 2 examples at any given point with the forward and backward pass through the model. Is this slowing down my training? And this becomes a really, really, really big consideration if you're wanting to train large models on very big data, right? And what it essentially happens is that we realize that training large language models is hard. So for any of you that have done this, you can really attest to this, and I've really tried to motivate this here. And that we haven't even considered, hyperparameter optimizations, which type of layers do you want to use, what type of attention techniques. There's no optimization specifics here. We're only talking about the architectural and like the system architecture and the engineering challenge you need. And what basically ends up happening in order to do efficient training and that you can maximize resources, we're going to have to move away from single GPU setups to sort of distributed or decentralized training that will inspire this federated direction, as I'll talk about later. So we're going to have to move to a stage where we have a single node that is comprised of multiple GPUs, where each of the GPUs are interconnected with fast interconnects, or we even go to multi-node setups with each node made up of multiple GPUs. And this, it becomes more and more difficult to train models, and this just increases with the requirements of the model, right? So as you increase the parameters, this becomes more costly. Now, the community in response to this has invented parallelism techniques that allow us to distribute our training on these multiple nodes. So there's 2 main branches, roughly. The first one is model parallelism, where we're thinking about sharding the model in sort of certain dimensions such that we can put parts of the model in different workers, and then the training is coordinated like this, where each worker has its own unique portion. Or we can do data parallel, where we're thinking about increasing the throughput of our system by making sure that each worker has the same copy of the data, sorry, not the same copy of the data of the model, but they're working on their own data, right? And this is just to increase the throughput, so we're processing more examples at one point. And this is really what both distributed data parallelism and the federated learning methods are targeting, at least in their motivation. This extends to different motivations later, right? So we're going to start now with what DDP actually is, so distributed data parallel. So what we can think of is we're trying to repeat the scenario that I've been talking about earlier, where we've arrived to a situation where I can fit the entire training loop so that the model can train on one device, but my batch size is very low. So the way to sort of simulate a larger batch size, you can obviously do this with gradient accumulation, but to parallelize it across workers, we can have the same training loop repeated over k workers, and then your effective batch size essentially becomes the batch size on your local device multiplied by the number of workers. Now, how DDP works in a nutshell is that each worker will get the exact model and its own data partition, right? Then each model will then sample a batch from its own unique data partition, do the forward and backward pass to obtain the gradients. Then right before taking a model step on that worker, there is an all reduce operation, which is essentially an average across all the workers to create a single gradient object that all the workers have. And why this is necessary is that now all of your workers are operating on the same information, such that when they take the same gradient step, they produce the exactly the same model, right? So we're syncing the results, and then we repeat this process throughout training, right, until we end training at some point. Now, how this works from an algorithmic perspective, we see that we have each of these processes P in parallel, where each of them samples a batch BI. They compute a forward pass, a loss, a gradient, and then there is this all reduce operation. So this averaging operation is within this processing unit, such that all the workers are now synced, and then all the models will take the update step on their local devices, which will give us the same model state across all of these workers. Now, this works surprisingly well, right? You can really get very far and really increase the efficiency of your training. And this is really well supported by modern machine learning libraries. So for those of you that haven't tried this out with PyTorch, I really recommend that you go and see the blog, because it's really well written and quite intuitive. And the number of lines of code that you have to introduce to do this is very limited. But with this, obviously, there's a trade-off. Now, since we're doing parallelism across number of workers, we've introduced this all reduce step. And this is very, very, very communication intensive, because every time we do a forward and backward pass, we need to do a sync across all the workers. And DDP doesn't, it only gets you so far, but if your model size scales above a certain point, DDP can't do anything for you, because the memory that you need to train is just too small. So you're going to actually need to do data parallelism combined with model parallelism. We're not talking about this here. Another issue that I'm sort of brushing over loosely is that when we do this all reduce across the gradients, before it, we essentially have a block where we're waiting for all of the workers to compute their gradients, and only then can we perform the reduce once we've received the full information across, in this case, the P workers. Now, this is essentially problematic because we would ideally want all of the workers to finish at the same time. And what this means is that these systems are not really well optimized for heterogeneous hardware, where certain workers are going to perform much slower than others, and we'll just introduce more latency here. So this is an aside as a sort of system side note, but it's I guess just worth thinking about, but it's not really the point of the talk that I'm making today. Right. Okay, so I think I can pause here if there's any questions. Harsh, I don't know if there's any questions on the chat. If not, I can just continue and start introducing the federated way of thinking.
Yeah, I think you go ahead. No questions in the chat.
Okay, right. So now that we have DDP, there is a seminal work that came out called local SGD. And you can actually think of local SGD and federated learning being the same thing. There are slight differences in sort of the assumptions that underlie these algorithms, but from a mathematical point of view and the proofs that you'll get, they're essentially the same. Now, why we want to use local SGD instead of, say, DDP, is that we want to alleviate the communication cost. And the way we do this is through decreasing the frequency of our communication. So this is on one axis, right? So I can reduce the communication just by communicating infrequently. Of course, another axis is, making the amount of your communication smaller, so the actual payload through quantizing, compressing in some way. But this is orthogonal to what local SGD is doing. So what local SGD says is that the averaging operation across the gradient is going to be pushed later. And what I mean by this is we're going to allow now each worker to progress for K rounds of local training in complete isolation from all the other workers. So we can see in the pseudocode here is that we have 8 rounds of local training where each model or each worker is proceeding in isolation from all other. Then finally, when all the workers finish their local rounds of training, we average the model state by just simply taking all the model parameters that have come out, average them, and we rebroadcast this new state to the each of the workers. And then this will proceed then for T rounds of global training. So you can also, this is also called communication rounds or global rounds. And this really works. I'll show this why this is done later, is because you can think about it as a double delayed optimization where you have an optimizer that is working internally on each of the clients, and then an optimizer that is working on the server when you're taking an average. So you haven't really broken any training assumptions here. You've just formulated in a slightly different idea. Now, another consideration that should be made here is that if the data that the clients are training on is very different, and you allow them to train for very, very, very long periods of time, the clients are going to go into very different directions, specializing to their particular data distributions. And this is known as data heterogeneity, where each of the clients have different data. versus homogeneity, where everything is the same, statistically speaking, across all of the workers. Now, in these scenarios where we're training language models, we're assuming that we have full control of the server such that we can assign data partitions that are the same across workers, so we don't really think about this being a concern for us. Of course, some of the other methods take this into account, and we'll have mitigation strategies for data heterogeneity, but this is another thing that could potentially make this very difficult. Now, going to why this works from a theoretical perspective. So the convergence properties of this algorithm was first proved by Sebastian Stich, where it shows that this federated learning or federated averaging or local SGD framework of training has the exact mini batch, so the same linear rate of speed up compared to mini batch SGD. So by communicating less frequently, you don't compromise, at least theoretically, on performance in any way, right? And again, what I'm talking about specifically of it being a sort of two-stage optimization scheme is because later the Fed opt work showed that these constructions of local SGD and federated optimization can be thought about being this double optimization, where instead of sending the model parameters, you're sending the pseudo gradient. So this can be seen on line 9, where the pseudo gradient is the difference between the model that you inherited from the server and then the final model that you produced at the end of local training. So effectively, this is the same object in some way, because it will be the same dimensionality as the model parameters, but you're just subtracting where you began. And now when you aggregate this in line 10 on the server, this becomes a pseudo gradient signal onto which the server takes a gradient step. And why this is really useful is that it gives us an opening where we can think about putting in different optimizers on the client and on the server to actually make more progress. And I guess it's a fun example for the reader to go through that in this framework, in the FedOpt framework, you can recover federated averaging if you set the client optimizer to be stochastic gradient descent, and then the server optimizer to be stochastic gradient descent, and you explicitly set the learning rate to be 1. Yes, so this is why these things really work. So this is from a theoretical point of view. Now, if we go to, sorry, I'm having a lot of trouble clicking here. For some reason, it's not working. So this is from a theoretical perspective. But if we start looking at a practical point of view, so how does this translate from theory to practice? These two papers, so don't use large mini batch, use local SGD, and why and when does local SGD perform better than SGD? There are actual, practical results showing that local SGD gives us better results than mini batch SGD. And we will see this in two forms. So sometimes we can have faster convergence, but one of the main things that we see is that we can achieve better local optima. And sort of two motivations that the community are giving for this is that these local SGD or federated style optimizers are reducing sharpness in minima, so they're actually able to make more progress relative to if you were just doing mini batch SGD. And what also turns out to be very true is that these federated or local SGD methods can scale to larger batch sizes more readily than mini batch. So what I mean by here is that when you increase the amount of batches that you're processing, you will eventually get to a plateau where increasing the batch size doesn't give you any more progress in terms of the final result that you're making. But this plateau comes much later, and you're able to process more batches, so essentially a larger throughput with local SGD. But, and I think I heard a question, so I'll pause here. The problem with all of these benchmarks is that it's on a particular type of problem. So these were vision benchmarks with relatively simple architectures, and stochastic gradient descent as an optimizer works really well. And this is problematic because this is not a language modeling task, and we know that stochastic gradient descent from other works does not really work on language modeling.
Yeah, I could read out the question.
Sure.
I'll remove the qualifier. It's not a stupid question. Can we integrate local SGD with something like pipeline parallelism to further reduce communication overhead?
Yeah, so I'll get onto this later with one of the works called Photon. But essentially, if we start thinking about in this federated constellation, your worker can be really anything. It can obviously be a single worker with a single GPU, but this can also be a worker that is comprised of multiple GPUs, where the local worker is sort of doing its own training strategy in parallel. So here you can put additional pipeline parallelism to make the model parallelism true here, or you can do tensor parallelism or fully sharded data parallel. So we don't really care what is happening on the local side as long as we can produce a model at the end after a certain number of local steps, and then we communicate this to the server. So of course, they go in tandem with other parallelism or compression methods because it's a different axis of improvement. Yeah, I think hopefully I've answered the question. Is there any more questions? No. Okay.
Yep.
Right. So some of you may ask and say, okay, since this federated optimization scheme that we see here in algorithm 1 is so flexible, and I'm being deliberately vague here because I'll show you why this might not be the case later. It seems as if we have ultimate freedom to just choose any client optimizer and every server optimizer we want, and training should proceed. So what I mean by here is that it seems sort of an obvious choice to say, okay, just plug in Adam as a better optimizer than SGD, just do training to produce your local model, and then proceed as normal. And now this is really great because now we can imagine doing localized LLM training tasks using AdamW and gradient clipping because we're going to need to normalize the gradient norms. And we can just average the model states at the end. And this seems to work, at least in an intuitive sense. And this is what really ballooned out to be the current state of the art that we're seeing using federated learning LLM training that we see now. And sort of leading these works, they were in parallel released. So the first one is called DeLoco, so it's quite famous on Twitter. So DeLoco is essentially federated learning training for LLMs, and there's a specific setup that they're using. But again, they come from this more DDP-like framework where we're assuming that we have full control of the data center and full control of the data partitioning scheme that we're going to be using. And what makes DeLoco special is that the authors of the paper found that the combination of AdamW locally and then also using stochastic gradient descent with Nestor of momentum on the server to be this ideal combination. So this is what, when you're using AdamW locally and SGD with Nestor of momentum on the server, this is what makes it DeLoco. Now, simultaneously, we had this work called Photon. Now, this is the work from the lab that I'm in, CamelSys. Photon showed that you can get very similar results if you're thinking about the strategy from a purely federated inspiration. And what differs from these two works is that Photon says we don't really want to touch the underlying data distributions. So we're assuming that the clients are sort of isolated from us in that they have isolated data partitions that are never shared with the global server, which is, I guess, different from DeLoco. Of course, you can put the same works in the same setting, but DeLoco assumes that you're sort of sharding the data and assigning data to clients, whereas Photon is going from the ground up. But ultimately, what Photon does, because they do IID experiments, so when you have data homogeneity and heterogeneity, what it ends up is that these two works are solving the exact same problem, right? But what Photon showed is that you can also do simple averaging and you don't need stochastic gradient descent with momentum on the server to get good results. Now, to focus on the results from Photon just for a moment, it actually becomes very surprising, right? Because at least up to this point, people didn't think we could train large language models being, at a really large scale across the internet. So the experiments in the paper used this sort of decentralized topology where we had certain servers activated in Utah, Texas, England, and so on. And each of the clusters were comprised of server-grade GPUs. Now, this is an asterisk I'll return to later. And we see that across the model sizes, right? So from 125 million to 7 billion, not only are we going to be able to match the performance of centralized training, in certain cases, we're able to beat it. Now, this was really surprising, at least for the authors when they were writing it, because it somewhat seems unintuitive that with this increased efficiency through communicating less and doing it over the internet with relatively slow connections, and slow here is with inverted commas, that we're able to get such great results at the scales at 7B. Now, what is really important to note here is that these good results are particularly in a setting where the federated learning scheme is using large batch sizes, which we've seen from previous work actually helps these local SGD and the federated average methods, right? So of course, this is used to highlight the results, but I think the point is made that you can make training completely decentralized and it works, and you can get good results and you don't compromise on performance. And not only has this been shown with Deloco and Photon, but also startups such as Prime Intellect are showing this, with live training runs, right? And you can actually monitor the training curves going down. And this is just very cool from someone that's interested in the field, and you see this progress being done. Now, another caveat that we have to note, which is the last point I was talking about here, is that the devices that are used in these experiments are essentially data center level hardware. So even though we are thinking about this being completely decentralized across the globe, we haven't made it such that, or at least in the experimental setting, we haven't made it such that we're using truly commodity level hardware, right? Where we're just taking gaming GPUs, donated from a couple of individuals, and then we're collaborating to train an LLM. So of course, the H100s not only cost money, but they have significant processing power and memory to support the training. So it is, while it's an encouraging result, there's still a little bit of work to do to try and make this, truly collaborative across, location, but also on the size of your data stack, of your machine learning stack. Right, so I think I'm going to pause again here, because now I'm going to be talking about some state-of-the-art research papers and introducing DeskLock, which is a method that I've been involved with.
I have a question, maybe. Though this is not something sort of specifically covered so far, but is there a tendency in these language modeling tasks as opposed to vision tasks where heterogeneity is not as much of a factor because it's all text in some sense? And the scale is so large of the original data set, where suddenly you're not getting the kind of heterogeneity that you would have in these toy tasks, or say even the vision tasks that we were looking at. So just curious about that part.
I mean, I think it obviously depends on to watch what LLM task you're modeling. So say that you're doing some classification task on the glue benchmark with SST2. It becomes very difficult there to define a heterogeneous split. Maybe you can do it across the labels, but it's still not truly heterogeneous, right? Because the underlying statistical properties don't really change with the labels. Of course, you can skew it, and this will alter the results somewhat, but it's not truly heterogeneous. Of course, then you can do some feature clustering where you're trying to isolate, certain training data points into different buckets, and then pushing these buckets out to different clients to create heterogeneity in this way. I think the golden sort of test for doing data heterogeneity in language modeling tasks is really when you're thinking about multilingual data, because of course you have statistical properties that may transfer across the different languages, but in essence, there is very unique attributes when you compare, let's say, Serbian, this is my mother tongue, relative to Afrikaans or isiZulu, right? They're very different languages, and of course, there might be some transfer, but the clients are going to be learning very different generalization properties for the different languages. And we'll touch on this at the very end as a sort of suggestion for further reading, where even though these heterogeneous settings exist, federated learning is well suited to tackle them as a modeling problem.
Sounds good. There's another question in the chat I'll read out. So maybe I missed, but could federated learning work with asynchronous updates, like with several batches delay,
Yes.
over internet distributed training is challenging not only for throughput but also large latency. So yeah,
Yes.
that's the question. Yeah.
Yes. So this is definitely true. So towards the end of the slide, on the slideshow, I'll highlight two works that have sort of done this. But also what needs to be said is that federated learning as a discipline has investigated a lot of these problems in isolation to language modeling. Because federated learning in its inception was invented as a privacy-preserving technique. And there was a whole host of methods that were invented in this realm, right? So different types of optimizers on the server, different aggregation strategies, how you prevent the clients from going too far from one another. But in a language modeling task, at least I don't know whether anyone has tackled this problem too explicitly, other than the two papers that I'm going to be mentioning. So of course, there's a bit of work to be done to translate all of the findings that we found in federated learning to language modeling, but I don't expect them to be too far away because in essence, the tasks are very similar. Okay, so right, to now jump into the state-of-the-art part of the talk. So I was talking about this very loose assumption of, we can just take any combination of inner optimizer and outer optimizer. So the optimizer that's on the server and on the client, and we can just plug and play and get any results that we want. But a big question actually emerges when we start using adaptive optimizers on the client. So a big part of what makes adaptive optimizers so successful is that they have these two momentum buffers that are sort of making sure that we're making great progress on training, right? And now if we think about these momentum buffers being unique to every client, how do we go about actually scaling our federated learning training as training progresses? So not at the initialization where the sort of model state doesn't matter, but maybe in the middle where we want to increase the batch size. Now, what we can do is sort of two things, is that we can reset the optimizer states at every round, right? So, irrespective of whether you're involved in training or not, you just reset the optimizer states and start from afresh. Or if you want to sort of maintain these optimizer states and introduce new clients, you can sort of ad hoc average these optimizer states such that the new clients have good information to progress with the model updates and not just start diverging because the random initialization isn't going to help them in their optimization direction. And what it turns out, there was this paper that recently came out at ICLR this year from Cheng and Glasgow, is that for provable convergence in these setups where you're using ADAM locally, and the paper terms this algorithm local ADAM, not only do you need to average the optimizer states, sorry, not the optimizer states, the model parameters, you need to average all the momenta as well. Now, this is sort of a shot in the foot for these federated learning methods because, of course, we're increasing the communication efficiency relative to DDP by communicating infrequently. The problem with this is that we have a 3x increase in the individual payload size that we're sending at the end of every local training round. Now, this is quite extensive if we're thinking about the scale of these LLMs that are, a couple of billion parameters and going to trillions. And this is not really a technical, cost that you really want to accrue during your training. So what our work, Deslock here, so this is work I was involved in, a whole bunch of collaborators. The local ADAM work is known to converge, and we even see that at least this is from a theoretical level, this is true. But how can we make this more efficient? So one way that we thought about is that observing the fact that the model parameters and the optimizer states are very different objects, so they behave very differently during training, can we assign independent sync frequencies to each of these objects such that, through this additional infrequency and syncing, we can gain in communication efficiency whilst maintaining provable convergence and robustness with our results? So this is the question we asked. And it actually turns out that you can, right? And the theoretical motivation for this is that if you look at the two ADAM momenta equations here at the top, we see that the optimizer states have a sort of unique half-life. And what I mean by this is that the larger you make your beta parameters for the respective two optimizer states, the more relevant the previous history remains for the length of your local training. And what this means is that you don't actually have to sync it that frequently. Moreover, if you're using gradient clipping, which is very important for LLM training, the absolute amount that your optimizer states are going to train is bounded, at least above, by the clipping factor rho that you use, and also the choice of beta. So the bigger you make beta, the smaller this absolute change is going to be. And we find that this actually gives us a theoretical foundation through which we can exploit some efficiency gains. And on the right-hand side here, we see that on typical toy problems for optimization, we find that local atom and DESLOC actually can converge much better to the local optima of different settings relative to methods that are either reinitializing this local state every round, which is the red one. Sorry, we are going forward here. The red one, versus methods that are trying to maintain the optimizer states, because these two sort of heuristic methods aren't provably convergent. And we found settings here, both in the IID and the non-IID setting on the bottom, that we found examples where this is the case. Right. So what DESLOC really is it's a family of methods that are assigning these independent sync frequencies to different optimizer states. So on the left, we see sort of the canonical formulation where we can generalize to any amount of optimizer states here on in line 14. So there's, say, n of them, right? So for any of the n optimizer states, we can index by j. We can have a unique frequency. And then we finally have a unique frequency for the parameters there. And then on the right, all this is that it's a particular instantiation of DESLOC made to Adam. So you can transfer DESLOC to any adaptive optimizer on the client. So, SGD with momentum, adopt, and so on. Right. So once we sort of made this theoretical argument, and there's actually what is really cool about this is there's a whole proof of convergence guarantees that you get to actually show that this, in fact, delayed frequency of syncing doesn't compromise on your convergence, at least theoretically. But once we've done this, we wanted to prove empirically that these rates of change of optimizer do hold throughout local training. And what we see here for two classes of local optimizers, so adopt and Adam, the second moment in the right column changes far, far, far slower than the first momentum. So what this means is that we can actually see that it doesn't change much. So we confirm, at least empirically, that we can sync it less frequently and that it won't harm our training progression. Right. Once we've sort of laid the ground for this, what we then wanted to check is that which of these sync frequencies is the most important and which is the relevant order that we have to order them, at least implicitly. So in the top left-hand corner, we see that the sync frequency of your parameters is the most important. And if you push the sync frequency too far, so in this case, we see that we have settings where, let's say, you set the sync frequency to 3072 local steps, your training completely diverges and you can't make any progress. So this is the most sensitive parameter, and in fact, the parameter that you have to sync the most frequently. And then what we see later, that no matter which setting of the first momentum and second momentum syncing period you're using, no matter how far you push it, you don't really change the progress you're making on your objective all that much, which is fantastic. But what it also means here is that implicitly you need to sync the first momentum more frequently than the second to get the best performance. And then you can also infer the syncing proportions of the momentum based on their half-lives, which is tied to their beta parameters. So it gives sort of a method of doing this. Now, what we end up seeing in this third research question, relative to local Adam, is that we can bring about a 2 times communication reduction compared to the local Adam without really compromising on training quality. So in all of these results, we see that DESLOC is actually able to track the training curves of local Adam and particularly have the same gradient norms, which is really good. So we know that training isn't exploding. But what is also really cool is that when you scale this training up to, I think in this example was 1.7 billion parameters, these insights still stay, right? So where heuristic methods really diverge and become quite unstable, Deslock is able to achieve within noise performance of local atom. But what is sort of a takeaway here is that we see that DDP is still achieving the best results, but if you use methods such as Deslock, you get a 170x reduction in communication relative to DDP. So it becomes really a question of trade-off, right? Like, are you willing to take a small cut in your performance on a downstream benchmark in contrast for an extreme reduction in your communication efficiency? So this is just Deslock at one point in how we try to improve this communication frequency. So to summarize, I'll sort of be now giving sort of different directions for future exploration and suggesting like different areas that people have been making progress of. So these are the two papers that are related to one of the questions that were put in the chat about how we can actually have improvements to latency where, we're having these periods where we have essentially a block where we're waiting for all the clients to complete their work, and then we have these averaging procedures. What these two works, so streaming DeLoco and then eager updates for overlap communication, what they both show, so at least in the first point, is what they show that you don't actually have to wait for all the clients to finish, but what you can do is you can actually overlap the communication and computation. And what this means is that when clients finish training, they can upload their model states and download the most fresh copy of the current model states from the server. And this happens sort of asynchronously, such that, when clients are finishing, they can upload their model quantities. The server takes, takes count of this information and makes progress on the server optimization. And you can actually do this without compromising on performance. Now, another point that this work shows in one of their ablations is that the actual updates you're sending don't have to be full rank model parameters. So what they show is that now this is the second axis that you can actually reduce the communication, is that you don't have to send the full model parameters, but you can actually compress them down without sacrificing your model performance. And I think they even get down to 8-bit in the experiments without, the performance, dropping too much. Of course, you can't go all the way down to 1-bit. This is not expected, but it's quite cool to see that, we can couple these efficiency techniques where we're doing, infrequent communication on one axis and then, other compression techniques on the other. So then another work, and now these papers are very new. I think they've come out in like the last week or two, and this is sort of showing how hot this research direction is that it isn't really clear what the interaction between the different optimizers are, right? And also whether averaging is the correct thing to use. So the first paper here, Muloko, shows that you can actually choose Mu1 instead of Adam W locally, and that you get much better performance, right? And this is also sort of echoing the recent hype about Mu1 generally as an optimizer and its performance in the NanoGPT benchmark. And then sort of relatedly to this, No Loco shows is that we don't actually have to have an all-reduced communication across all of our workers, but we can actually do gossip communication where we're communicating with us within a certain neighborhood of devices and not everyone. So this, of course, again, is going to reduce the communication efficiency. And this paper shows that you're actually able to get really good provable convergence and good results on underlying benchmarks. Now, what I finally want to highlight here is that even though these methods are sort of really cool from an efficiency point of view, and I guess this has been the focus of the talk, this is related to the question that Harsha asked earlier, is that how do we start thinking about truly heterogeneous data training or decentralized training? And what I want to argue in this paper that's come out of the group that was actually an oral at ICLR, it argues that moving away from centralized to decentralized frameworks of training is the way to go if we really want to make the next step in advancing our field forwards. This is a very large claim, but the reason for this is as follows. So the general motivation is that sort of the next frontier of data is private data, because we're reaching to a point where we can no longer scrape any more public data from the internet. So we're going to need to start tapping into these private data sources. And one of the ways we can do this is through leveraging federated learning with additional privacy-preserving techniques such as DDP and, not DDP, differential privacy or secure aggregation, for example. But what also happens is that if you switch to this federated learning way of thinking, you can reformulate the problem in many interesting ways. So what happens in the case of transformer training for multilingual problems here in this paper is that the problem, at least one of the problems in multilingual model training for LLMs, is if you want to have a shared embedding matrix for all of your languages, this embedding layer is going to be very, very, very huge, because you actually need to have it to cover a lot of tokens to cover the training for all of the languages you want to have in. But if you do federated learning training, where each client is assigned a unique language, you can actually have a situation where you assign independent embedding matrices to each of the clients, such that these independent embedding matrices are very small relative to that client, and you don't actually have to communicate them in training. So you can leave them frozen on the clients and only train the transformer body, which is sort of this, shared information that transfers well across languages, and the clients can make benefit of this. And what these frameworks show, and you can go in the paper and see the results for yourself, is that you're able to get very good personalization on each of the languages, whilst making this, much more efficient for training, and sort of alleviating some of the difficulties with multilinguality. And I think, at least I share this sentiment, my group shares this sentiment, and a couple of other people in the field, that this is really the next frontier of where we need to make progress going forward with machine learning. So finally, just a conclusion slide. So what this has been is a sort of historical overview, a sort of signposting to relevant works that have been coming out in this field. And this is work that has come from many different avenues. So it's not just academic researchers or companies, but it's even like startups that are doing this in the wild. And while we have really, really good results so far, I think there's a lot of work left to be explored. So just putting on a couple of examples here. So we need to really figure out what is going on between the server optimizers and the client optimizers, and how these interact, because we don't really have a paper that talks about, let's say, the scaling laws of what to use when and what is the best. Also, a completely different axis we haven't talked about is compression, and how do these compression techniques that we're normally using in different areas, how do these transfer to these large scale, both in the number of parameters and the number of nodes that we're thinking in federated learning training. And then the real task now is to scale to like even larger architectures, and this is quite an interesting challenge from an engineering point, but it's also quite exciting. So this is the end of the talk. Yeah, I'm happy to stick around and chat off away from the recording, and then answer any questions that people may have. But thank you for the opportunity to talk, and thank you for your attention.